This is an audio reading of the paper Effective Use of Large Language Models for Social Constructivism in Computer Science Education, written by Nicholas Faulkner of Adelaide University, Leo Lepinen of University of Jyväskylä, Juho Laininen of Aalto University. Narrated by Nicholas Gardella of Washington and Lee University. This paper is published in the Proceedings of the 31st ACM Conference on Innovation and Technology in Computer Science Education, Volume 1, ITICSI 2026. This conference was held in Madrid, Spain, in July 10th to 15th, 2026. The license for this work is a Creative Commons Attribution 4.0 International License. The copyright is held by the authors. Abstract. Novice CS students can have a very wide range of starting knowledge. Bringing students to a professional level of practice requires an active process for students to develop their skills and knowledge individually and collaboratively. Through the use of social constructivism, a theory of learning based on the benefits of collaborative social interactions between learners, these interactions allow learners to develop their knowledge by making sense of the interactions. This can take many forms, including discussing concepts, working on collaborative projects, and receiving timely and accurate feedback from their peer group and supervising instructors. The gap between what a learner is capable of doing without support and what the learner could perform with the assistance of a more knowledgeable other, MKO, whether peer or teacher, is defined as the zone of proximal development, ZPD. Recent advances in chatbot technologies, especially those based on large language models, LLMs, and various institutional incentives, naturally guide focus toward AI agents' potential as participants in collaborative social interactions. In this paper, we identify the characteristics and affordances of LLMs in how they might successfully support a computer science students through the ZPD, drawing on existing theory across key disciplines and knowledge of the characteristics of LLMs. We propose a group of models for constructive uses of this new technology, which will support social constructivism well and provide more general guidelines for the use of LLMs. 1. Introduction. Social constructivism is an important theory of learning based on the perceived benefits of collaborative social interactions between learners, where these interactions allow learners to develop their knowledge by making sense of the interactions. Social interaction, exposure to different ideas and levels of knowledge all contribute to the learner constructing their own knowledge as they understand how it all makes sense. Supportive, scaffolded environments allow a learner to obtain a greater level of knowledge than what they would be able to attain working alone. The area between what the learner is capable of independently and what the learner is capable of with adult assistance or the help of a more capable peer is referred to as the zone of proximal development, ZPD. Group discussion and reflection remains an important part of computer science education, whether in software engineering, project discussions to understand concepts, pair programming, code reviews, or in larger discussions in professional spaces such as ethics or professional practice. With growing class sizes and increased threats to knowledge development such as code writing, AI engines, we have the joint issue of needing to have more group discussion activities to drive understanding with fewer resources. The growth in AI-related technologies in recent time has been immense, with more assistive agents, chatbots, and invested resources than at any earlier time, all having a substantial impact on the way we look for information, aggregate information, write pieces of work, and even write code. LLMs have become heavily used in the co-writing or complete writing of pieces of code for assignment submission. And given the relative simplicity of the classes of grammars that are implemented as modern programming languages, it can be far easier for a student to submit generated code and escape detection than to write long, semantically and grammatically rich, longer pieces of text. Earlier work indicates that the process of cognitive offloading that such use of LLMs enables, where the student does not conduct the thoughtful exploration themselves but passes the actual task to a third party, can lead to a measurable decline in the level of critical thinking displayed by students. Often, student development in computer science depends on the development of their programming abilities, their ability to interface between algorithm and implementation. Thus, this growing use of LLMs is a key concern. Can we address both the need for group members at scale and our need for learning boost through using some of the new AI technologies in place of other students or staff? Pre-trained language models use transformer models trained over large corpora to develop systems that can solve a number of natural language processing problems. with large language models being the term for the largest and most complex of these, which can be capable of solving quite complex problems. In this paper, we investigate the key literature on ZPD and explore how current large language models such as ChatGPT could be used with students to facilitate social constructivism in a reliable and ethical way. 2. Background. In examining social constructivism, we note Vygotsky's work was essentially with children, and while, as with Piaget, we have carried this knowledge development over into older student phase, there are lingering influences. Vygotsky's definition of the ZPD is not detailed in describing the nature of guidance and collaboration that is going to promote development beyond that which the individual is capable of. Peers without a guide tutor, for example, children without an adult, can at most attain limited success. Unsupported learning lacks direction until the students gain enough knowledge to be able to synthesize new steps, a significantly higher level of knowledge and intellectual development. The more knowledgeable other, MKO, an adult or tutor, is an essential element of the beneficial application of social constructivism, both from Vygotsky's original work and from further exploration. But how does an MKO interact with learners? We know that a well-chosen and competent partner can provide a benefit, but a partner at a barely superior level is of much less utility, and a bad partner is worse than none at all. Scaffolding was originally proposed in separation from the more general construct of the ZPD, but was identified as an important answer to the question of what functions the MKO would effectively provide to develop the ZPD in learners with a social constructivist setting. Scaffolding takes many forms, but includes recruitment to the task, orientation, highlighting critical features, demonstrating goal achievement, and managing frustration. Scaffolding is a dynamic, learner-centric, and changes based on the progress on the task and the task itself. This responsiveness is essential in that the MKO is constantly evaluating and then calibrating levels of support. This support tapers off when not needed, much as how scaffolds are removed as building becomes more strong. Thus, it's not merely the presence of an MKO that can provide the benefits of the ZPD. That individual must provide key requirements of knowledge and support, and provide that support in a way it can be removed as the learner shows their independence. Recall that the ZPD is the area between what the learner can achieve independently and what they can achieve with support. Having achieved the new level with support, we must remove the supports. Then we can build the new ZPD that takes the student further, reintroducing new scaffolding in a different area. All of this assumes that the student has conducted the relevant work themselves and that their knowledge construction, personally and in the group, is around knowledge and skills that are specific to the topic of interest. That is, there is a cognitive demand made by the topics and materials being studied. Cognitive offloading refers to relying on the environment external to the student to reduce the cognitive demand, which can be as simple as writing a note to avoid having to remember something in our memories. Cognitive offloading allows the student to avoid doing any relevant work to achieve the outcome, where examples include copying solutions, work for hire, and use of tools that can generate the correct output without the requisite knowledge. The prompts used to generate code examples and solutions from large language models are an example of a cognitive offloading mechanism, as a student can request code in a given language with a set of characteristics and not know how to develop the algorithms or write code. Cognitive load is an essential lens for viewing the role of scaffolding in its reduction of load while students are developing the schemas that will form part of their long-term retention and thus impact their behavior. Significant cognitive underloading is a known issue in the tasks that students can perform, and that are less likely to lead to positive outcomes from a social constructivist perspective. The correct level of challenge must be present to ensure that social constructivist activities occupy the ZPD. Unrestrained cognitive offloading risks reducing the level of load too far. While there's a level of requisite attentiveness and desire to solve a problem together that creates cognitive, social, and emotional interchanges in groups, LLMs have no training or capacity to support the genuine social and emotional aspects. This social aspect is essential in social constructivism, as Vygotsky argued that learning could not be separated from social context. Piaget referred to this necessity of the societal as, quote, excessive biosocial optimism, end quote, but agreed with many of Vygotsky's fundamental statements. Vygotsky and Piaget disagreed on exactly what children got from groups. Vygotsky felt that adults transmitted the culture's tools of intellectual adaptation for them to be internalized by children, whereas Piaget felt that peer interaction led to social perspective. Arguments for both exist, usually in the nature of cultural touchstones versus de facto culturally located normative roles. While Vygotsky's analysis is far less categorical than Piaget's stages, his approach is heavily role normative, requiring key players in the exchange rather than monitoring where the participants are in their development phase. The use of LLMs proposes changing the nature of one of the most important roles, the MKO. Vygotsky's experimental methodology was based on two stimuli, the first of which provided the learner with a problem they were unable to solve with the tools they presently possessed, and then a second stimulus that could be used as a tool to solve the problem. This solving of the problem, or applying the second stimulus to the first, can be viewed as a process of remediation. In a social context, where the learner is not simply handed a suitable tool and instructions on how to use it, but instead must identify whether a potential tool is the right one, the learner's ZPD is defined by the degree to which they can identify and apply the right tool. Social constructivism is far more than the adjacency of more and less knowledgeable participants. Social interaction, group management, and support are all important part of successful interaction. It's not enough to put a subject matter expert, even a reliable one, into a group and expect every student's ZPD to open up for new knowledge construction. 2.1. Essential requirements of MKOs. What are the characteristics of a successful MKO? Tools themselves have been argued as functioning as MKOs if we consider them as embodying knowledge that guides learners. Consider the example of fraction strips guiding children's understanding of a fraction addition, without direct instruction from an adult. This suggests that the design of affordances of tools could structure learning experiences, creating a ZPD where learners, through their interactions with these tools, can achieve more than they could independently. However, there's no guarantee of fading this support, which goes against the scaffolding principles that were discussed previously. There's no adaptation based on the development of knowledge. The tools by themselves could be considered a component of the support provided by an MKO, similar to computers. See reference 36, but appear to lack the necessary roles that an MKO can take. The ZPD is not static and cannot be if knowledge growth is to continue. We must expect the ZPD for the individual learner to shift as they learn. The MKO has to reduce scaffolding as the learner advances in their knowledge, which in turn maintains the delicate balance of cognitive load. The requirement for fading clearly distinguishes an interactive MKO from a fixed tool. The MKO must have knowledge in the relevant area, an understanding of the task at hand, be able to explain and model the task, and be able to manage the knowledge flow to address frustration and cognitive load. We accept that human MKOs are not guaranteed to be perfect, and the availability of sufficient staff to support these activities is an ongoing issue for many institutions. However, the authors assert that the careful selection and training of MKOs is a known requirement for effective student support, and the human MKOs are both capable of iterative development of a previous answer, as well as being less prone to hallucinating random answers. There's an implicit assumption regarding the different levels of knowledge between MKO and learner, in that the MKO needs to be aware of the learner's level and act accordingly. Without this, the interaction is likely to be less successful because they will not be able to explain, model, or manage at a suitable level of their participant audience. We focus purely on cognitive development, as one of the criticisms of Vygotsky is that his focus on cognitive knowledge, not emotional knowledge or development. While we discuss managing flow to address this frustration, there's no implied emotional bonding or support that is provided as a requirement of social constructivism. While we're using the frame of cognitive development, we recognize that intrinsic load reduces with repeated exposure, which increases the effective capacity of working memory. But this assumes that the processing to the exposure is carried out by the student and not offloaded. We know we want MKOs, but often we have a very large number of students to manage, which is where we could usually turn to tool-based support to address our needs. Can recent developments in generative AI and large language models provide the interactive and effective MKOs that we need to support student development in the ZPD at a large scale? 2.2. Characteristics of LLM operation. Historically, LLMs have been less successful with domain-specific response generation due to the nature and availability of training data. In the area of knowledge completion, the prediction of the missing elements of a piece of knowledge, LLMs are prone to hallucination, where they give incorrect answers that can either directly contradict something they have been told, intrinsic, or they produce an answer that is incorrectly based on stored knowledge, extrinsic. The training cycle required to develop an LLM also leaves them vulnerable to issues with knowledge recency, as the distance between training time and current time grows. But these are not the only issues, as there's no semantic encoding for the data that has been used to build the model, and thus the LLMs are also prone to reasoning inconsistency and struggle with numerical operations. While it's possible for an LLM to give the correct answer to a problem, reasoning inconsistency then means that the justification given can be incorrect. Even where the solution space is grammatically simpler, such as programming language solutions for short artifacts, a, quote, correct appearing, end quote, solution may still have no solid reasoning support, as the reasoning occupies a far more challenging solution domain. Many LLMs are also heavily stochastic in their output, and what is given as a solution to a prompt may change with the reissue of the identical prompt, even where iterative change or detailed inspection and explanation were requested. Solutions have been sought for the issues around depth of knowledge and domain-specific responses have been improved through the use of retrieval augmented generation, RAG. But the training time and costs are non-trivial, and the models are still prone to providing answers when there is not enough information to do so. Agentic approaches promise outputs that are more likely to be correct through a layered approach, but are very resource intensive and can add even more layers of obfuscation as to why a particular answer was given. We note that an LLM may be capable of successfully handling any of these roles. It is not guaranteed to the degree that we might want. There is an implicit assumption that an MKO remains an MKO throughout the interaction. Any system or approach that does not allow this may cause problems. In the next section, we discuss approaches that still allow the use of the power and capability of LLMs in the ZPD, but with limits that restrict problems. 3. Considerations. In the previous section, we identified clear risks posed in the development of knowledge with learner groups. Unless we're sure that we can address these risks or match or exceed them with benefit, it would be unethical to conduct an experiment from the current framing. To support this, we discuss cognitive biases, in particular, primacy and recency biases. The primacy bias is a cognitive bias where the first knowledge that we discover about a new topic tends to become more highly valued and persistent than what we learn later, to the extent that we may reject future efforts to change it. The recency bias is another cognitive bias where we favor what we have recently learned or what is fresh in our minds. The damage posed by an unreliable MKO is now clear given social constructivism is focused on the development of new knowledge through sense-making of what is transmitted in the social setting. An unreliable, unwittingly, and indifferently incorrect MKO could lead students to develop incorrect assumptions about knowledge, giving an impression of having attained the higher level of knowledge possible in the ZPD. Worse, having this expectation is now harder to change and fresh in the student's mind. The way that an LLM is used is critical here, as code-focused LLM that just produces code which does not work easily and immediately detectable because the code does not work, although subtly incorrect produced code could still lead students down, quote, debugging rabbit holes, end quote, see reference 40, or distract students from their programming process. The longer-term damage to the student is the potential disruption of the cognitive processes required to learn effectively in this environment, due to the cognitive offloading implicit in any use of LLM prompt-based solutions to develop code. The trap here is that LLMs can produce workable answers to short, commonly asked coding questions in well-known languages, but this robs students of necessary experience in developing foundation concepts using simple monothematic coding solutions. By the time that a program has reached the level of complexity that LLMs start to produce poor results, the worst-case cognitive offloading outcome is that the student has no recourse but to keep reissuing a prompt for a different version, as they have no long-term recollection of the foundational and developed aspects of programming. An LLM in the middle of a discussion about theory or explaining a complex concept can do far more harm if it hallucinates or just mishandles the explanation. A novice learner may simply not have enough knowledge to know what they are learning from the LLM is wrong. Indeed, it has been found that just giving learners access to, quote, industry grade, end quote, LLM tools such as ChatGPT or GitHub Copilot can lead to a, quote, widening gap, end quote. See reference 30, where well-performing students, for example, those with more prior experience, are able to leverage the tools effectively, similar to professional developers. But the students who are already struggling to use it ineffectively, accepting buggy or hallucinated suggestions from the AI without understanding the code. This, combined with the student's tendency to not verify code produced by an LLM, see reference 2, and at-risk students, those with lower grades, higher fear of failure, and lower self-efficacy, being both more inclined to use AI in the first place and use it earlier, can lead students to developing an illusion of competence where they think they're progressing in the task as code is being produced when they are not. Again, any skill developed is in promoting the skill that they should be learning, rather than learning the target skill. In addition, it's been found that when coding with AI tools, not only do students face the same metacognitive difficulties as before, but some are exacerbated by AI tools, and there are entirely new difficulties introduced by AI, such as AI suggestions interrupting the student's train of thought. In the next section, we propose some models for LLM use that reduce the risk while still allowing usage within our ethical restrictions. For learning to happen, we must have a posed problem and then interactions and remediation in the act of solving, which we previously identified as first stimulus for the problem and second stimulus for the following interactions. This is a useful separation between the generation of materials, problems, and the interaction with students around that, including feedback, knowledge sharing, and everything else. A first stimulus has value even if the problem contained is of low knowledge value or even nonsense, as the student's consideration of that leads to the exploration of current knowledge. There is little risk that a student will learn anything incorrect from this, as the synthesis of the implied knowledge would be required prior to then learning the incorrect knowledge, and this is very likely to be developmentally beyond the students if this is a new knowledge area. Our primary concern for LLM characteristics expressed above are when these systems are active in the context of the second stimulus, the interactive space where knowledge construction can take place through the sense-making of shared interactions. We refer to both stimuli components as we discuss the way forward, but note the immediate result that any LLM could be used in a problem generation, reducing workload and allowing for more personalization, as long as a human handled the interactions afterward, supplying the necessary load framing to ensure there is correct level of cognitive load. 4. Ways forward. There are still ample opportunities for the use of LLMs in education. We have identified some of them here, recognizing the state of the art and the requirements of social constructivism. They are LLMs as participant but not MKOs, LLMs as supporter of the MKO, and LLMs as a teaching example. We note that LLMs by their nature do not have an innate physical presence in a face-to-face setting and are much more likely to be potential participants in a virtual classroom or online discussion forum. 4.1. LLMs as non-MKOs. Key weaknesses of LLMs relate to their use as the MKO, a purportedly reliable source of correct and valid information and logic, and the pace setter for the learning experience. Perhaps the simplest way to work around those specific issues is to employ LLMs in some role other than the MKO, such as a simulated peer. For example, in reference 19, where it was proposed to use simulated peers in software engineering education, or even a, quote, less knowledgeable other, end quote. For example, in reference 26, where ChatGPT was used to simulate students in teacher training, or to acknowledge their weaknesses and use them via moderation. Some recent research suggests that LLMs can be guided to produce code that is similar to student code, so it's not too far-fetched that they could be guided to act as peers. Similarly, LLMs can sometimes provide explanations of code that students find useful. These explanations can be useful if they are framed as coming from a peer, not an MKO, for students to critically evaluate them. While reframing the role of the LLM as a non-MKO would not solve all problems relating to LLMs, it would effectively turn any factual or reasoning mistakes from a bug into a feature. Students might expect their peers, even if simulated, to make mistakes, while they likely expect responses from a, quote, teacher to be correct. Figure 1 shows the role of the LLM as a support to an MKO who filters the results of LLM queries to provide reliable, knowledgeable support to a learner group. For example, responding to student help requests with the instructor or teaching assistants as the MKO filters. While the relationship between the LLM and the MKO is shown in a single arrow, obviously the MKO could pass student queries back to the LLM in order for them to filter any responses. The MKO here has explicit pedagogical knowledge that is used to provide, quote, pacing and support, end quote, noted in the label of their relationship back to the student group, capturing load management concerns. Figure 2 shows the LLM as a participant in the group, as a simulated peer or less knowledgeable other. This artificially expands the group size, providing more reactions to student comments, with the MKO moderating the content and discussion to ensure that the information generated by the LLM does not dominate if they had become an in-group MKO. This model also provides an opportunity to train teaching staff in the management of students in group, with the caveat that the LLM group member may be unintentionally disruptive due to the characteristics of hallucination and non-deterministic responses. The LLM also has no cognitive processing delay compared to other participants and may potentially intimidate by answering very quickly or confuse by providing answers that change on every utterance. One question raised when we introduced LLMs into a group discussion is whether we need to inform students that their group member is not another student but an LLM. We usually have an inherent obligation not to deceive our students, and in some cases, an institution's policies may either forbid or allow limited deception under very well-defined conditions. But can we expect similar interactivity if we define two categories of group participants or clearly label one or more group members as, quote, other, end quote? LLMs have no emotions or cognitive capacity to be offended, which focuses this decision on what the benefits will be for the other students and teaching staff in this interaction. There's a subtle difference between identifying an LLM participant as a fellow student by name and by having an anonymous participants in the discussion, some of whom may be LLMs, but it's an open question as to whether it's still deceptive, and if it does not meet our ethical requirements to the students to deal with them honestly. In general, the decision as to whether this is valid is likely an institutional decision pending the development of greater guidelines on best practice presentation of LLM identity. 4.2. Limiting LLMs. Natural language generation, NLG, can be and has historically been conceptualized as consisting of several distinct subproblems. For example, we can view language production as consisting of a task where the information content of the message being generated is determined, another task where that information is linearized and structured into sentences and paragraphs, a third task where linguistic expressions, words, etc., are associated with the information content, and finally a surface realization task where the words are turned into their correct grammatical forms, for example, declension. So-called end-to-end systems, such as LLMs, that completely forego separation into multiple tasks are relatively latecomers into the field of NLG. One potential route forward is to actually look backwards and consider whether we need to do all of these tasks via LLMs or in one step. NLG literature contains many works investigating, for example, neural two-stage architectures that could serve as promising starting points for future works that delegate the LLM to tasks where its main weaknesses are not able to manifest. Figure 3 shows a model where the task separation of an LLM combined with output filtering can lead to a system that is more limited than a full LLM, but potentially more reliable in knowledge delivery and provided with enough pedagogical structure that support and pacing components of an MKO can be approximated. After reference 13, the three terms in the diagram refer to the NLG components of LLMs, specifically the analysis of relevant corpora with the determination of the syntactic structure and the association of existing information with that structure. but not the generative components of LLMs that could lead to problems. 4.3. Teaching students about LLMs and their roles. Another potential solution is to explicitly teach students about the limitations of LLMs and try to help them understand the potential role that LLMs can and cannot play in their learning, with the LLM completely exposed in any interaction. If responses from the LLM are not provided as authoritative feedback, i.e. not as replacements for instructor feedback, but as comments more akin to those from peers, students may examine them more critically. Figure 4 shows an open usage of LLM where an MKO is still present to provide the pedagogical support that is not intrinsic to an LLM's responses, as well as providing confirmation and moderation in an environment where students are encouraged to question what comes from the exposed LLM. As noted earlier, nothing in the design or deployment of LLMs addresses the cognitive load concerns that we have in general in establishing the ZPD. There's still a mismatch between the possible speed of response and the availability of an LLM and a human MKO. If students work at times at which the human MKO is not responding, then a number of queries may be answered by the LLM without any oversight, which reduces the amount of time that students may spend in trying to solve the problem, which again interferes with the cognitive load environment that a well-designed environment should have. Given the known issues of primacy and recency bias, merely warning students of the possible issues with answers provided by the LLM may not be sufficient for them to avoid adding incorrect information to their knowledge base. Furthermore, if a sufficient amount of LLM responses are, quote, correct enough, end quote, constant warnings giving rise to warning fatigue or the, quote, cry wolf effect, end quote, and learners ignoring these static warnings completely. But as always, there may be no way for a student to interact with an LLM without causing longer-term knowledge construction and retention issues due to cognitive offloading. This provides a solid foundation for more research into exactly what is the best way to address these issues around solution reliability and the offloading problems without greatly improving the reliability and capabilities that manage LLM responses. Given the dependency of computer science education on programming, and given the early indications that offloading can have an impact on critical thinking and interfere with long-term retention, it is not just the fundamental mechanisms of LLMs that need to be improved, but the environmental containers that limit the impact they can have on vulnerable learners. 5. Conclusion. In this proposal paper, we have presented mechanisms for how large language models, LLMs, could potentially be used to support students' learning examined through the lens of ZPD originally proposed by Vygotsky. We have identified that, given the relative ease with which LLMs can generate small code artifacts, early programming of the type found in CS1 courses is a possible area where overuse of LLMs could lead to cognitive offloading and hence reduce the level of learning that we seek to have. Thus, while LLM usage is an issue for everyone in education, computer science is particularly vulnerable as we have both heavy early tool users in the technological space and we depend heavily on programming knowledge in our later courses. We argue that LLMs, or their responses, should not be presented as an authoritative support due to their inherent limitations, for example, tendency to hallucinate, which could negatively influence students' learning, as they may expect that this type of support is an MKO and hence reliably correct. But it is not just for their unreliability that LLMs fall short. They are not capable nor trained to provide the support that is required component of an effectively social constructivist space and have no concept or ability to control cognitive load levels. This is beyond the demands of the ZPD and is as simple as, quote, understanding that sometimes delaying a response is a crucial component of student learning because we want the student to think for longer, rather than have a piece of software that is unintentionally incorrect but always immediate. We would rather have one that was accurate and deliberate in its timing and word choice to encourage student knowledge construction. Thus, we have provided examples of LLM-based or supported systems that address these issues. In addition, we propose that LLMs could play roles where their responses are not expected to be authoritative, such as simulated, less knowledgeable peers. We have identified the vulnerability of the student as they're learning new material, arguing from knowledge of biases and ethics, as well as a model of the role of working memory and scaffolding, that there is an inherent requirement for an MKO to meet certain criteria, which LLMs currently cannot. Yet the immediate response to this is a question of whether every human who attempts to fill the role can do this. This is a valid question, as it provides incentive to ensure that all of our staff are knowledgeable and well-trained in the relevant skill sets and discipline if we are to argue that LLMs are worse for not meeting the criteria. While we have addressed the ethics of identifying LLM use in social constructivism, we have not identified the potential power issues around MKOs, who usually hold more dominant position in the group. How does this translate to LLMs? We believe that there's a great deal of possible future work in this area, especially in the exploration of student perceptions of, quote, synthetic group mates and the perceived and actual learning gains provided by LLM-supported MKOs, as well as pseudo-MKOs who are chatbot variant less likely to cause negative effects. As authors, we're keen to engage with the community on the ethical aspects of this, as we believe that there's a great deal of good work to do. There is little argument that generative AI and LLMs will continue to be a part of the educational landscape, and we are not by any means suggesting that they not be used. However, the theory is quite clear on what is required for certain roles in certain types of learning environment, and it is equally clear that unfettered direct access to LLMs is not the best way to meet these role requirements. We believe that there are constructive ways to continue to use these technologies while still providing the best possible support for our students at crucial points in their knowledge development. Acknowledgements. This work was supported by Research Council of Finland, Grant 356114. This is your narrator here. I just wanted to give a quick reaction to the paper. My name is Nicholas Gardella. I'm an assistant professor of computer science at Washington and Lee University in Lexington, Virginia, USA. So first, I just wanted to give my impression of what this paper was about. Then I'll mention what I thought some of its strengths were, a few things that were confusing to me, and some interesting assumptions I noticed that I think would warrant further exploration. So my understanding of this paper was it was heavily based on the work of Vygotsky about the zone of proximal development and the concept of the more knowledgeable other functioning in computer science education as a peer or a teacher who is teaching another student a concept that they want to learn in computer science education. And they have this concept that AI can't be an MKO. That's sort of their argument, because it isn't reliable enough to help students to formulate their understanding of a topic based on some sort of learning activity. Maybe, however, it could be useful for other aspects of the learning process if we don't place it as the more knowledgeable other. So they recommend one approach would be to have this sort of patriarchal control over the AI, where the TA or the professor is the MKO. They are the teacher of the students and they have the control, but they can then communicate to the AI on their own, to the LLM, get some output on the full spectrum of the LLM's capability, and then filter that material down for something that is correct and reliable, whatever that means, for the students. Their second recommendation was you could use the AI as a peer. So basically, we don't necessarily trust the output of the LLM as being reliable, but we also don't trust students to necessarily be reliable. So if we can have the student to act as a peer, whether we tell the students that it is a peer among them, or whether we sort of deceive them or hide from them that one of their peers is an LLM, then we don't have to worry about the AI being wrong, because we can just have a commentary about why that was wrong and use that as a teachable moment. The third option was to essentially use it, but only use components of NLG or natural language generation technology to do some kind of components of this process. So for example, we can understand the structure of a student's problem or of a topic area or the learning activity, the assessment, whatnot. We can associate that with relevant information in the broader field, and we can use this as a tool to kind of understand the problem and how it relates to larger knowledge structures, but we're not necessarily going to allow the LLM to directly generate the full spectrum of its response to the students. And I'll touch on this more later because you can hear in my reaction that I'm a bit confused and challenged by trying to explain the difference between this recommendation and the first sort of patriarchal option of the TAs and the professors control the AI and the students go to them. And the third, well, I guess so that was the second option. And then the third option was to just let students have access to the LLMs, but then as a secondary teaching aspect, the MKOs can communicate with the learner groups, the students, to help them to understand that AI is not perfectly reliable, and they can have those interactions for themselves, but they're getting a little bit of guidance on the side to not just be completely assuming that the LLMs are perfect. So the strengths I noted down from this paper were the mentioning about Vygotsky's work, and Piaget for that matter, being about childhood development and not really being about computer science education for university students. That's something that most people who bring in this citation and talk about zone of proximal development, in my experience, do not acknowledge the book Mind and Society, where this is talked about. Not only is it a kind of smaller component of the book than you might assume from how it's cited, it's also about children, and it's not really super detailed. And the authors here do a good job of mentioning, like, hey, this is where this idea comes from, but it doesn't perfectly elaborate on in all the ways that we'd like. So they sort of offer an interpretation of what it means in this context, in terms of what it means for like an MKO or a TA, a professor, another peer who's teaching a student, or an LLM, what it means to offer help to a student. And they mention the aspects that it might be good for and why it might not be good. So they kind of use hallucination or unreliability as the primary discrediting factor for an LLM, why it can't be the MKO. But they also have a nice insight that there's a requirement for this MKO process where a student learns from a more knowledgeable other, that the MKO helps the student in the challenging part of the thing that they've never done before, that they've not understood before. But then they also step back progressively and allow the student to progressively take over in one given area of inquiry or activity. So working on a let's say a level 1 programming challenge, and then stepping back to where the student is doing a level 1. Now we're going to a level 2 where the student has mastered level 1 and they're now going to be pushed at a level 2, and then the MKO will step back at level 2 and allow them to move to level 3. And that's kind of a necessary piece that the authors are saying the LLM is lacking. So because it's just taking away the cognitive process of experiencing the given level that the student is at, that it never steps away. And that is like a critical component of this theory about ZPD. So that was a great insight. And then they also mentioned this 2 stimulus paradigm. So where an MKO is teaching an LKO, there's an initial stimulus, which is the learning activity. So like we're coding, we're working on a programming task, and that is a stimulus. But there's not really an importance about how high quality that stimulus or that material is. For example, we can have a perfectly implemented piece of code and we can use that as a stimulus 1, or we can have a code with errors and problems, and that can be a teachable moment because we can teach about the errors and how to avoid those errors and how did that come about and why someone made that mistake. But then there's a second stimulus, which is the MKO guiding the student through the interaction with the with the stimulus one and then connecting it to the larger knowledge structures. And that's really where the authors say LLMs are not good, where we want humans to be doing that level 2 because we don't have the reliability with the LLMs to be doing that. And so it's fine if they create type 1 stimulus where it can be wrong, but it's not okay if it creates the type 2 stimulus where it's reconciling the stimulus 1 having been right or wrong. The other strength I noted was recognizing the limitations of mediating MKOs. So for example, their first recommendation being the LLM talks to the human MKO and the human MKO talks to the students. So in this, we're kind of saying, okay, only the TA gets to access the LLM, and they're going to use it to help produce learning materials or to help with processing student requests for support or something, but it's always going to be filtered through them to do that like stimulus number 2 with the students. And they recognize that there's this limitation by suggesting that it's not really that realistic. You say, oh, you can only use our special educational AI, or you can only the TA can use AI and you have to go talk to the TA. Well, what happens in off hours, unsupervised learning, where the students go and they just use ChatGPT to their heart's content? The authors mention this as the cry wolf effect, and how, students will find that LLM responses are correct enough, especially on these simple problems that they're doing. And so if they're being told that it's, you can't use this, it's dangerous, it hallucinates, and they're not finding that to be the case in their unsupervised experience with it, then they're not really going to buy into this system where the TA has to be the middleman between you and the LLM. It's just kind of unrealistic. So it's great that they recognize that limitation and offer one of their suggestions is letting the students interact directly with the LLM, because the reality is that's going to happen even if you say in an ideal world it wouldn't. A couple of things that confused me. One was when they mentioned the distinction between the theories of Vygotsky and Piaget. I think maybe it's because I'm more familiar with the work of Vygotsky why this confused me, but specifically this paragraph on page 211 that goes, Vygotsky and Piaget disagreed on exactly what children got from groups, so on and so forth. The sentence, arguments for both exist, usually in the nature of cultural touchstones versus de facto culturally located normative roles. While Vygotsky's analysis is far less categorical than Piaget's stages, his approach is heavily role normative, requiring key players in the exchange rather than monitoring where the participants are in their developmental stage. This took me a while of reading and rereading to understand what's being said here. And I think the point is, hey, this paper is mostly about Vygotsky and his framing of this idea that you can be the MKO or the LKO in this dynamic. You're either the student or you're the TA, whereas Piaget was more saying like you develop through these specific stages of development that have to do with your age. And essentially what they're saying is, hey, there are other scholars that kind of think in a similar way, but really we're focusing on Vygotsky. So that's my only takeaway from this. And overall, I found the bringing in that commentary was a bit confusing without a little bit of very plain conclusion of like, wait, why are we dwelling on the similarities and differences between those two theories here? So I'm still left a little bit confused and probably would take a bit more rereading to understand what the purpose was there. The other piece that was confusing was this section that I mentioned before about limiting LLMs and this bringing up NLG, natural language generation, as a broader field, I suppose. this was trying, I think, to distinguish the concepts displayed in figure 1 versus figure 3. So in figure 1, it goes LLM to MKO, MKO to learners. In figure 3, it goes LLM to MKO, but also to pseudo MKO, and then MKO to pseudo MKO, and pseudo MKO to learner group. And that last sentence I tried to pick apart, says after reference 13, the three terms in the diagram refer to NLG components of LLM, specifically the analysis of corpora, the determination of structure, the association of existing information with that structure, but not the generative components of LLMs that could lead to problems. So I'm not sure I understand this, because maybe there's some later component, or it's this whole chain together that an LLM just kind of does all the NLG tasks at once. That's the problem. But I'm not exactly picturing how you would implement, and I wish the authors had developed this a little bit more, because it's an interesting idea, but I'm still left a little bit confused about where it was going. So what tasks do we give to the NLG sub pipeline, where we're only using the analysis tool, or we're only using the structure tool, or the information association tool? I think that can make sense. I'm just not understanding exactly how do we take a student query, or a learning task, or a textbook chapter, or whatever it is that is the teaching medium, the stimulus number 1, and use the LLM for that without it being essentially just the same as figure 1, where it's LLM to MKO, MKO to learner. I think developing that idea more would be interesting, because that's definitely a useful approach. And I think that kind of touches on something they very briefly mentioned, which was this new fad around agentic coding, and that maybe agentic coding is more reliable, in a sense that the LLM has access to tools, and it can sort of try something and see the output and fail and try again, and work iteratively in that way to be more reliable. But the authors mentioned that there's sort of a cost to that. It takes a lot of tokens to iterate on a problem, and it's potentially wasteful. So those are a bunch of ideas that just weren't really addressed, because I guess they were out of scope. But it would be interesting to consider, how can you divide up the role of the LLM into a smaller piece that is more reliable. And this gets into some of the assumptions that I noticed in this paper, and then also, therefore, what is out of scope as discussions that weren't really touched on that are still useful to think about. So there's this very key assumption in here. I felt that the human is blessed and the AI is cursed. So we can trust a human instructor to be the MKO or a TA, but we can't necessarily trust the AI, because it experiences hallucinations. And so that is, the AI is not perfectly reliable, and then the human maybe is. But is that true? I don't know. I mean, certainly we hope the educators are pretty reliable, but I think there's two things that are concerning about that assumption. One is that humans aren't perfectly reliable. Sometimes the human instructors make mistakes. And then the other thing is that the AI is not perfectly unreliable. It is sometimes quite correct. And as the authors mentioned, you could have the cry wolf effect, where if you tell the students it's unreliable, when they find that it is reliable, they won't believe what you're saying about the LLM. So in reality, the LLM is, some percentage reliable and fails in some percentage of the cases. And that's also a moving target. As we get into the future, more and more, the reliability will get higher. And maybe a better way to think about this is not as human reliable, AI unreliable, but as both human and AI are unreliable in different ways at different times. And both of them, the number is not going to be 100%. Maybe we can't even measure it. And that kind of gets into something that wasn't addressed here, which is what is correctness? What is reliability? What does it mean for an MKO to give proper stimulus to support to a student. I think that's up for debate. Even if you consider two faculty members in the same department as teaching the same course in different ways, they may be able to argue for hours about their approach and why their approach is best, but there's not necessarily an objective reality about whether what they're teaching is better or worse. Now, there are certain things that are just factually incorrect, and hallucinations are a way that can produce factual inaccuracies. You could say that Python 3 supports X feature that it in fact does not support. But again, that's a mistake that both a human and an LLM could make. And maybe there's a larger philosophical discussion about where we're less accepting of the same mistake made by an LLM as compared to a human. We also, how do we judge it? We can't really judge correctness on an objective scale. So are we going to say that this particular output of the LLM, if it's not something so obvious as a factual inaccuracy, are we going to say that this approach, because we didn't like it for some reason, does that mean that it was a wrong stimulus to support? I think that would be up for debate in a case-by-case basis. And so it's a little bit maybe unfair to just say the AI is cursed and that it can't be the MKO. Something else that's not addressed, that's definitely out of scope, is do we even need to learn the things that this whole paper is centered around trying to get students to be able to learn. So like they need to be able to learn simple programming problems so that they can move on to the upper division classes, as they mentioned in the paper, to work in those more complex areas and be competent professionals or whatnot, whatever the goal of education is. But there's kind of an open question about if AI can do simple things for us, why not let AI do those simple things? If it can do more complex things, why not let it do those more complex things? Maybe our only role as humans is just to decide what we want and let the AI take care of the implementation. Then again, that opens environmental concerns and monetary and efficiency concerns. And what's the best approach to do something if you have multiple options? That being human can do it or AI can do it. And you need to think about that at a larger systems level, but this is not something that they contend with at all. They sort of operate on this assumption, like, yes, education is designed to make students learn these things, and so we're going to investigate how we can best support that with LLMs. So a good thing that they did is just they take that stand and then they don't have to equivocate about that problem while they talk about their proposed solutions. But the challenge is, okay, but that still maybe needs to be addressed, and this whole conversation could be for nothing if the question or the basis is like irrelevant. So I think that pretty much summarizes this. I think it's the most maybe interesting idea that I can see here is considering the LLM as a peer and saying, well, if we can't trust it, let's just assume we can't trust it and treat it like that. And it's an interesting participant in the learning experience, even if we maintain the traditional model. But realistically and unfortunately, we probably have to be more attentive going forward to this figure 4, this last 4.3 section of, okay, well, the learners are going to interface with the LLM on their own without us as mediators, as educators. So we're just going to have to do some stimulus to support for them that gives them the tools that they need to critically evaluate LLM outputs, considering that they're not perfectly reliable. You've just listened to the paper, Effective Use of Large Language Models for Social Constructivism in Computer Science Education. This paper is a copyrighted work, with the copyright held by the authors. It's licensed under a Creative Commons Attribution 4.0 International License. The reflections you've heard are original contributions by me, Nicholas Gardella, your narrator. Thank you.